Question 1. In the context of diagnosing a performance degradation in a production Oracle 12-app database, Ista Patel notices increased D time, but the CPU usage remains stable. What should Ista Patel primarily investigate to identify the root cause of the issue? A. Wait events and event classes to find bottlenecks. B. Shared pool memory allocation for potential fragmentation. C. Optimizer statistics freshness to ensure accurate query plans. D. Size of the buffer cache to reduce physical I/O. Answer. Correct answer. A. Explanation. DB time includes time spent waiting and CPU processing, where CPU is stable but DB time rises. The system is likely waiting on resources, making wait events the primary diagnostic focus. Wait events and their classes provide insight into which resources cause delays, whether I/O locks or latches. Shared pool fragmentation, optimizer stats, or buffer cache size can impact performance, but typically affect CPU usage or physical I/O metrics. Hence, analyzing wait events helps pinpoint underlying resource contention and wait event bottlenecks, aligning with Oracle's best practices for performance diagnosis. Question 2. Given the circumstances, Lopez is tuning SUL queries that consistently perform poorly despite recent optimizer statistics refresh. Which action should she take to improve execution plan stability without altering the application code? A. Create SUL profiles to influence the optimizer decisions. B. Increase PGA size to allow for better sorting and hashing. C. Rebuild all indexes to optimize access paths. D. Use SUL trace and tkiprof to analyze past times. Answer. Correct answer. D. Explanation SQL trace and tkiprof provide detailed insight into SUL parsing, execution, and wait times, helping identify inefficiencies such as repeated hard passes or suboptimal execution steps. While SUL profiles can influence optimizer decisions, they require specific tuning after detailed analysis. Increasing PGA or rebuilding indexes might help but don't directly address the root cause. Query instability. Proper use of SUL trace and tkiprof enables granular diagnosis to determine whether the problem lies in parsing, execution, or wait events, supporting informed optimization steps. Question 3. From the perspective of using automatic workcode repository hour reports, what is the best approach to detect a gradual performance regression over several days in a critical system? A. Compare consecutive snapshots focusing on high EP usage. B. Analyze baseline comparisons of system-level wait events into SUL. C. Review session-level statistics for all active users in real time. D. Monitor redo log switches and archive log generation rates. Answer. Correct answer. D. Explanation. Redo log and archive log rates reflect transaction volume and can signal workcode changes contributing to performance shifts. However, for detecting gradual regression, comparing our baselines focusing on wait events and SQL trends is most effective. EPU alone might not highlight subtle regressions, and real-time session stats lack historical trend context. Therefore, reviewing IO baselines centered on system wait events and top resource-consuming SUL statements provides a comprehensive historical perspective to detect gradual performance degradation patterns effectively. Question 4. During the process of performance tuning, Ista Chen finds that certain SUL statements have different execution plans on similar workloads after a database upgrade. What mechanism should he implement to guarantee consistent execution plans for these statements? A. SUL plan management (SPM) with SUL plan baselines. B. Rebuild the data dictionary to reset statistics. C. Flush the shared pool to remove cached cursors. D. Increase the frequency of statistics gathering on tables. Answer. Correct answer. C. Explanation. Flushing the shared pool clears cached execution plans but does not guarantee consistent future plans. It only forces reparsing. Increasing stats or rebuilding the dictionary affects plan quality but not stability. SUL plan management with plan baselines preserves known good plans, preventing plan regression across upgrades or optimizer changes. Hence, SPM is the industry standard approach to maintain plan stability by allowing only verified plans, ensuring repeatable performance without requiring application changes. Question 5. when considering tuning the program global area PGA in Oracle 12ec, which factor most critically impacts the efficiency of memory-intensive operations like sorts and hash joins? A. Size of the automatic shared memory management pool. B. Configuration of the PGA aggregate target parameter. C. Allocation of the buffer cache to store frequently accessed blocks. D. Use of SUL profiles to optimize query execution paths. Answer. Correct answer. B. Explanation. The PGA aggregate target directly controls the amount of memory available for private session work areas such as sorts, hash joins, and bitmap mergers. Insufficient PGA size leads to increased use of temporary table space and disk I/O, drastically degrading performance. Shared pool and buffer cache address different memory areas, library cache and data blocks respectively, while SUL profiles optimizer decisions, not memory allocation. Proper PGA tuning is crucial for operations heavily reliant on in-memory processing, improving performance of complex SQL operations. Question 6. Considering the evidence from recent performance diagnostics, ATMA needs to prioritize actions after receiving an ADAM report suggesting contention on latches and mutexes. What is the most effective initial step to address this contention? Increase the redo log buffer size to reduce contention. B. Investigate and tune high-frequency SUL statements holding latches. C. Reorganize tables and indexes to improve EO efficiency. D. Disable automatic workload repository snapshots to reduce overhead. Answer. Correct answer. D. Explanation. Disabling our snapshots is not recommended as it impairs diagnostics. Increasing redo log buffer size or reorganizing tables impacts EO but not latch mutex contention. The root cause of latch contention is often hot objects such as frequently accessed shared pool structures or SUL statements. Investigating SUL holding latches too long or inefficient parsing can resolve contention. Therefore, problematic SUL to reduce latch holding times or redesigning SUL to avoid hotspot contention points aligns with ADAM recommendations and Oracle's performance tuning methodology. Question 7. Based on the information available, Kumar notices that some sessions are consistently waiting on DFIS scattered read wait events. What does this indicate about the nature of the SUL workload and how should he address it? A. The sessions are performing full table scans and consider adding indexes or optimizing SUL. B. The sessions are waiting for latch access due to shared pool fragmentation. C. The buffer cache size is too large, causing excessive physical EO. D. The redo log files are undersized, causing log switch waits. Answer. Correct answer. A. Explanation. DFIS scattered read indicates physical EO for multi-block reads typically during full table scans or large index range scans. This suggests SQL is reading large amounts of data and efficiently. Adding appropriate indexes or rewriting queries to use index access paths can reduce physical EO and wait times. Latch contention and buffer cache size affect other wait events, while redo log sizing impacts log switch events. Addressing full table scans through indexing or SUL tuning directly targets the root cause of these wait events. Question 8. For many years, Robinson has been tasked with setting performance baselines in Oracle 12ec to detect anomalies in production workloads. Which best practice should she apply to ensure meaningful and actionable baselines? A. Establish baselines during periods of typical workload without major system changes. B. Set baselines only after significant upgrades to capture new performance profiles. C. Use baselines generated during peak load times exclusively. D. Rely solely on average CPU usage statistics for baseline creation. Answer. Correct answer. C. Explanation. Baselines created during peak workload times represent the most critical performance periods and help detect deviations impacting users most. While typical workload periods are also useful, peak times ensure alerting on critical performance degradations. Setting baselines only after upgrades ignores normal operations, and relying solely on EPU is insufficient as other metrics like wait events, ITIL. Effective baselines incorporate multiple metrics across representative workloads, facilitating proactive performance management aligned with Oracle's monitoring principles. Question 9. In what ways can the Oracle SUL Tuning Advisor assist? A. When a complex query is running slower than expected on a 12-vec database. A. It automatically writes the query for better execution plans without DBA intervention. B. It identifies SUL statements for potential tuning and recommends statistics or indexing changes. C. It increases memory allocations dynamically to speed up execution. D. It defragments the buffer cache to improve data retrieval speeds. Answer. Correct answer. D. Explanation. The SUL Tuning Advisor analyzes SUL execution plans and resource usage, recommending actions like gathering statistics, creating SUL profiles, or adding indexes. It does not write queries automatically or adjust memory parameters directly. Buffer cache defragmentation is not a function of the advisor and is managed separately by Oracle. The advisor assists DBAS by providing targeted recommendations based on query analysis, helping optimize performance systematically within Oracle's framework. Question 10. Mr. Dias is configuring Oracle Database Resource Manager to control CPU allocation for a critical reporting service that often causes contention. Which approach should he adopt to prevent this service from impacting all transactions? A. Create a consumer group with a limited CPU percentage and assign reporting sessions to it. B. Increase the CPU count allocated to the database server hardware. C. Disable the resource manager to allow all sessions equal CPU access. D. Increase shared pool size to improve CPU scheduling. Answer. Correct answer. B. Explanation. Increasing hardware CPU count may improve overall capacity but does not isolate or control CPU usage per service. Disabling resource manager removes control, risking contention. Shared pool size affects memory, not CPU scheduling. Creating a consumer group with restricted CPU usage for the reporting service is the recommended approach to allocate CPU fairly and prevent salvation of all workloads. This aligns with best practices for managing workload priorities and maintaining system responsiveness. Question 11. Given the circumstances, is Ramirez observes a sudden spike in buffer cache misses and physical reads during peak hours. What should she prioritize to reduce physical EO and improve performance? A. Increase the buffer cache size to hold more frequently accessed data blocks. B. 2 SUL statements to reduce parsing overhead. C. Just the PGA aggregate target to optimize sort operations. D. Use SUL plan management to lock execution plans. Answer. Correct answer. A. Explanation. Buffer cache misses and increased physical reads directly indicate insufficient buffer cache size or inefficient data access patterns. Increasing buffer cache size allows more frequently accessed blocks to remain in memory, reducing disk I/O latency. While SUL tuning and plan management improve execution efficiency, they don't immediately affect physical reads caused by cache misses. PGA tuning impacts session memory. Unrelated to buffer cache. Proper buffer cache tuning is a fundamental step in minimizing costly physical EO and optimizing performance under heavy workloads. Question 12. When analyzing the active session history, Ash Istasingh finds a large number of sessions waiting on buffer busy waits. What underlying issue should he investigate first to resolve this contention? A. Excessive recursive SUL executions causing library cache locks. B. Hot blocks in the buffer cache due to concurrent DML orations. C. Redo log file size being too small causing frequent log switches. D. Poorly designed indexes leading to full table scans. Answer. Correct answer. D. Explanation. Buffer busy waits occur when multiple sessions simultaneously attempt to access the same data blocks, often hot blocks under heavy DML activity. Poor indexing can cause full table scans, increasing contention for certain blocks and exacerbating buffer busy waits. Recursive SUL causing library cache locks affects parsing, not buffer waits. Redo log sizing influences transaction logging latency but cause buffer contention. Addressing indexing inefficiencies reduces physical EO and contention hotspots, improving concurrency and overall throughput. Question 13. From the perspective of SUL plan management, which statement best describes how SUL baselines help maintain performance consistency during database upgrades? A. Baselines capture execution plans and allow only verified plans after upgrade, preventing regressions. B. Baselines force the optimizer to use full table scans regardless of statistics changes. C. Baselines automatically increase shared pool size to improve parsing efficiency. D. Baselines disable adaptive cursor sharing to reduce overhead. Answer. Correct answer. A. Explanation SQL baselines are a core feature of SUL plan management that store accepted execution plans. After upgrades, the optimizer might generate new plans that perform worse if baselines prevent this by allowing only verified, stable plans to execute. This safeguards against performance regressions. Baselines do not force specific access methods arbitrarily, nor do they alter memory allocation or disable adaptive cursor sharing. Their role is to stabilize execution plans, ensuring consistent performance without requiring application change or manual intervention. Question 14. In light of recent developments, Mr. Al-Mansouri is reviewing an report showing an unexpected increase in log file sync weights. What could be the most probable cause, and what should he focus on first? A. Inefficient SUL joins causing excessive CPU usage. B. Insufficient redo log buffer size causing frequent log flushes. C. Network latency between rack nodes causing delays. D. Contention on redo log writes due to frequent commits. Answer. Correct answer. C. Explanation. Log file sync wait events represent the time session waits for redo to be flushed to disk after commit. Network latency in rack environments can delay confirmation of commit writes, increasing these waits. While redo log buffer sizing impacts flush frequency, it rarely causes sustained high log file sync waits alone. Inefficient SUL joins affect EPU but not commit waits. Frequent commits increase log events but a workload characteristic rather than a tuning target. Therefore, investigating network latency or EO subsystem delays is crucial to reduce log file sync waits in rack setups. Question 15. Considering the evidence from VSysStat, is Johnson notices high pass count hard, so values correlated with slow application response times. What is the most effective approach to reduce these hard passes? A. Use bind variables and cursor sharing to promote cursor reuse. B. Increase the database buffer cache size to hold past statements. C. Disable SUL plan baseline to allow new plans. D. Enable SUL trace to capture past details for manual tuning. Answer. Correct answer. C. Explanation. Hard passes occur when the database must fully pass an AIR statement, which is costly and reduces performance. Using bind variables and cursor sharing effectively reduces hard passes by reusing cursors. Increasing buffer cache doesn't affect parsing directly, and SQL trace is diagnostic but not direct solution. Disabling SUL plan baseline is counterproductive because baselines help stabilize and prevent forced reparsing. The best immediate approach is to ensure application uses bind variables and proper cursor sharing, reducing parsing overhead and improving performance. Question 16. Based on the information available, Mr. Wang needs to analyze real-time performance issues affecting a batch job running unusually long. Which Oracle feature should he use to capture detailed session activity without impacting performance significantly? A. Use SUL tuning advisor to automatically optimize batch job queries. B. Query active session history hash views for session wait and activity sampling. Increase the PGA aggregate target to reduce disk spills. D. Enable full SQL trace for the batch job sessions. Answer. Correct answer. D. Explanation. SQL trace captures detailed information about SUL execution but can significantly impact performance if enabled indiscriminately. ASH provides sampled wait and session activity data with low overhead, ideal for real-time diagnostics without heavy impact. SQL Tuning Advisor suggests improvements but does not capture session activity directly. Increasing PGA affects memory, but not session-level diagnostics. Therefore, ASH is the best choice for low-impact real-time performance analysis, enabling focused problem identification in batch jobs. Question 17. While examining a workload replay, O'Neill notices that SUL statements consume more CPU than expected. Which feature helps predict the impact of system changes on SUL workload performance before production deployment? A. Automatic Database Diagnostic Monitor ADAM. B. SUL Performance Analyzer SPARS. C. SUL Access Advisor. D. Automatic Workload Repository Hour. Answer. Correct answer. A. Explanation. Adam analyzes historical performance data and provides recommendations for tuning but does not simulate system changes. SQL Performance Analyzer (SPART) is designed to predict the impact of changes by replaying workloads and comparing performance before deployment. SQL Access Advisor recommends indexes or materialized views to optimize access paths, while our collects and stores performance statistics. SPA uniquely enables what-if analysis of system changes on SQL performance, helping DBAS prevent regressions proactively. Question 18. To illustrate this point, ISTA-White is tuning, a database with frequent temporary table space usage due to large sorts. What is the most effective tuning strategy to reduce temporary space contention? A. Increase the size of the shared pool to hold sort operations in memory. B. Increase the PGA aggregate target to accommodate larger in-memory sorts. C. Create additional redo log groups to speed up logging. D. Gather fresh optimizer statistics on temporary table spaces. Answer. Correct answer. C. Explanation. Temporary table spaces are used for sorting where PGA memory is insufficient. Increasing PGA aggregate target can reduce physical temp space usage by enabling more in-memory sorts, but it must be balanced with overall system memory. Increasing shared pool size has no direct effect on sorting. Redo log groups improve logging throughput but do not reduce temporary table space contention. Gatherings on temporary table spaces is unnecessary as they do not hold permanent data. The PGA tuning is the direct lever, while redo log improvements support transaction performance, not sorts. Question 19. Under the assumption that certain SQL statements run consistently with varying execution plans, which approach best helps to stabilize performance without modifying SQL code? A. PySQL profiles to provide optimizer hints and statistics corrections. B. Rebuild underlying tables and indexes to refresh data layout. C. Enable SQL trace for detailed execution path analysis. D. Increase the database buffer cache size to reduce physical I/O. Answer. Correct answer. B. Explanation. SQL profiles influence optimizer decisions by correcting cardinality estimates or adding hints, stabilizing plans without code changes. Rebuilding tables and indexes improves physical layout but does not guarantee plan consistency. SQL trace is diagnostic but not corrective. Buffer cache tuning affects physical I/O but not plan stability. Therefore, applying SQL profiles is the recommended approach to guide the optimizer toward consistent plans, reducing variability and improving overall SQL reliability. Question 20. Taking into account the increasing load on the system, ISTA-Thomas wants to configure proactive alerts to detect early signs of performance degradation. Which Oracle feature should he primarily use? A. Enterprise Manager M performance pages to monitor metrics visually. B. Automatic workload repository I snapshots for historical trends. C. Metric thresholds and alerts configured in Enterprise Manager or a DBMS. SQL Tuning Advisor to optimize poorly performing statements automatically. Answer. Correct answer. D. Explanation. Metric thresholds and alerts enable automated monitoring to notify DBAS when performance indicators cross predefined limits, allowing early intervention. Enterprise Manager performance pages provide visualization but are passive monitoring tools. Our snapshots store historical data useful for trend analysis but not for real-time alerts. SQL Tuning Advisor suggests improvements but does not proactively alert. Hence, configuring metric thresholds and alerts is the best proactive approach for early detection and response to performance issues. Question 21. While examining an OR report, Gupta observes that the EU time is low, but DB time has increased significantly. What is the most plausible explanation, and what should she investigate? A. Increased wait events indicating resource contention. B. Inefficient indexing leading to excessive CPU use. C. Large PGA usage causing memory swapping. D. Excessive hard parsing impacting shared pool. Answer. Correct answer. D. Explanation. DB time is the sum of CPU time plus wait time. When eEPU is low but EB time rises, it signals more time is spent waiting than in CPU. Common causes include hard parsing causing contention and delays in shared pool operations. Inefficient indexing or PGA usage generally increases EPU I/O but not this specific pattern. Thus, investigating hard passing frequency and pull bottlenecks helps identify causes behind increased DB time despite OCPU aligning with Oracle's tuning methodology. Question 22. Mr. Fernandez is tuning database experiencing frequent log file parallel write waits during heavy OLP workloads. What is the best initial step to mitigate this problem? A. Increase the size and number of redo log files to reduce switch frequency. B. Optimize SUL statements to reduce CPU consumption. C. Tune the buffer cache to reduce physical reads. D. Implement SUL profiles to stabilize execution plans. Answer. Correct answer. C. Explanation. Log file parallel write waits occur when redo records are flushed in parallel to multiple disks. Excessive waits indicate EO bottlenecks in the redo subsystem. Increasing log file size and number reduces switch frequency but not flush wait times directly. Optimizing SUL or using profiles affect CPU or plans but do not address redo write bottlenecks. Buffer cache tuning indirectly impacts EO by reducing overall workload but does not solve redo write waits. The best action is to investigate and optimize EO subsystem supporting redo log files. Question 23. From the perspective of ASH analysis, Mr. Silva wants to identify the root cause of performance degradation linked to frequent latch contention. Which approach would provide the most actionable insight? A. Analyze high-frequency SUL statements holding latches for optimization opportunities. B. Increase shared pool size to reduce latch contention automatically. C. Disable ASH sampling to avoid overhead. D. Rebuild indexes to minimize data block contention. Answer. Correct answer. D. Explanation. ASH samples session activity including wait events like latch contention. While analyzing problematic SUL helps, latch contention often stems from internal structures or hot data blocks causing contention. Rebuilding indexes can help if the contention relates to data block access. Increasing shared pool size might help shared pool latches but won't fix all latch issues. Disabling ASH removes vital diagnostic data. Thus, focusing on index and data structure tuning is key to reducing latch contention. Question 24. Given the circumstances, is Kim notices inconsistent SUL execution plans after gathering new optimizer statistics. What strategy best preserves plan stability during statistics refreshes? A. Is SUL plan baselines to control accepted execution plans. B. Flush shared pool to remove old plans, forcing new ones. C. Disable adaptive cursor sharing to force plan reuse. D. Increase the optimizer index cost parameter to favor indexes. Answer. Correct answer. A. Explanation. SQL plan baselines store verified plans to ensure the optimizer chooses only stable plans after stats updates or database changes, preventing regressions. Flushing shared pool forces repassing, not stability. Disabling adaptive cursor sharing can degrade performance by reducing plan adaptability. Changing cost parameters can bias plans but does not guarantee stability, hence using SUL plan base is best practice to maintain consistent execution plans amid statistics changes. Question 25. While reviewing system performance, Mr. O'Connor observes high physical EO weights during full table scans. What is the most effective approach to reduce these weights without extensive schema changes? A. Implement table compression to reduce data size and EO. B. Increase redo log buffer size to improve transaction throughput. C. Adjust PGA target to better handle sort operations. D. Create more indexes to avoid full table scans entirely. Answer. Correct answer. B. Explanation. Physical EO weights during full table scans indicate heavy disk activity. Table compression effectively reduces storage in EO by decreasing data size, improving scan speed without schema redesign. Increasing redo log buffer improves transaction logging but does not affect read EO. Adjusting PGA benefits memory operations, not EO weights. Creating indexes may help but can be expensive and always practical. Compression offers a balanced, non-invasive method to reduce physical EO during scans. Question 26. As illustrated by recent ASH reports, his Diaz identifies long waits on ENC, TX, row-lock contention during peak batch updates. What tuning steps should she prioritize to reduce these weights? A. Reduce batch update size to lower transaction contention. B. Increase buffer cache size to speed data access. C. Rebuild all indexes on the updated tables. D. Increase PGA target to improve sort performance. Answer. Correct answer. C. Explanation. Row lock contention arises when multiple transactions try to modify the same data concurrently. Rebuilding indexes can optimize lock management and reduce contention by improving access paths and clustering. Reducing batch size lessens concurrency but may not be practical. Buffer cache tuning improves read efficiency but not locks. PGA affects memory-bound operations unrelated to row locks. Addressing in structure and transaction design is key to resolving lock contention issues indicated by ASH. Question 27. Under the assumption that SQL queries are unexpectedly slow after migrating to a multi-tenant architecture, what should White focus on to tune pluggable database PDBs? A. Analyze and tune PDB-specific resource plans and throttling settings. B. Increase instant PGA size to benefit all PDBs. C. Disable SQL plan management to force new plans. D. Rebuild indexes in the root container. Answer. Correct answer. A. Explanation. In a multi-tenant environment, each PDB can have its own resource plans controlling EPU and EO allocation. Tuning these plans optimizes resource distribution and reduces contention. Increasing PGA affects instance-wide memory, but may not resolve PDB-level issues. Disabling SQL plan management risks plan instability. Rebuilding indexes in the root container doesn't impact PD-specific performance. Therefore, focusing on PDB-level resource management aligns with multi-tenant tuning best practices. Question 20. By evaluating SQL trace outputs, Bennett detects frequent wait events related to EDB file sequential read. What is the most likely cause and best tuning approach? A. Excessive index range scans causing many single block reads. Consider index tuning. B. Inefficient full table scans causing high I/O write queries. C. Network latency delaying data retrieval. D. High CPU usage due to complex joins. Answer. Correct answer. C. Explanation. DB file sequential read indicates single block reads typically from index access paths. High frequency suggests many index lookups or random reads often linked to excessive or inefficient index usage. The best approach is index tuning or query rewrite to reduce unnecessary single block reads. Network latency and CPU do not directly cause this wait event. Full table scans generate multi-block DB file scattered read, hence focusing on indexing efficiency addresses this wait event effectively. Question 29. Taking into account the performance reports, Stuart wants to establish performance baselines for a new OLP system. Which practice ensures the baselines provide meaningful performance benchmarks? A. Capture baselines during steady-state workload periods with typical transaction volumes. B. Set baselines only after major patches are applied. C. Create baselines during system idle times to minimize noise. D. Use historical peak load data exclusively for baselines. Answer. Correct answer. A. Explanation. Baselines should represent normal, steady-state system behavior to provide realistic performance benchmarks. Capturing during typical transaction volumes ensures baselines reflect expected workload characteristics. Creating baselines only after patches ignores pre-patch performance. Using idle time skews baseline lower, causing false alarms. Using only peak data may misrepresent usual operations. Baseline capturing supports proactive detection of anomalies aligned with Oracle's performance monitoring guidance. Question 30. The fundamental question is, Aon wants to proactively monitor long-running database operations in real time. Which Oracle feature is best suited to track and analyze these operations? A. Real-time database operation monitoring, or TDOM, for continuous observation. B. SQL Tuning Advisor for query optimization suggestions. C. Automatic Workload Repository IA for historical snapshots. D. Enterprise Manager Performance Pages for manual review. Answer. Correct answer. A. Explanation. RADOM is designed to monitor long-running operations in real time, providing detailed progress and performance metrics that enable immediate intervention. SQL Tuning Advisor suggests optimizations but does not offer real-time tracking. I stores historical data, useful for post-mortem analysis but not real-time. Enterprise Manager visualizes performance data but relies on user action and is less suited for continuous automated monitoring. Oradom's proactive approach aligns with Oracle's emphasis on timely operational awareness.